Alright, hey guys, I've had a few requests to redo this video because it was hard to understand. And so, let's go. Consider the combination of resistors shown in the figure below. So here we have a set of resistors, and starting here at point A, if we go over, we can see that there are resistors in parallel, a resistor in series, and another resistor in parallel. Part A says find the equivalent resistance between point A and point B. So if we could just mush all of these into one resistor, what would the resistance have to be to get the same resistance across the entire thing? So let's zoom in here really quick and talk about how that works out. So we know that whenever resistors are in parallel, we can get the equivalent resistance. So we'll call that this is the equivalent resistance, resistance EQ1. The equivalent resistance at part 1 is going to be equal to, we'll call this resistor A, and we'll call this one resistor B. And so it's going to be equal to the inverse, so 1 over resistor A plus 1 over resistor B to the negative 1 power. So that means basically I'll add 1 over 12 plus 1 over 6, and then I'll flip that over. So I got 1 over 12 plus 1 over 6. That's going to equal a total of 3 over 12. Now I got to take that to the negative 1. So that means it's going to equal the equivalent resistance, the REQ1, is going to equal 12 over 3. In other words, this is equal to 4 ohms. Let's do the same thing for so we'll call this resistor 2, and then we'll call this, when we smash these together, we'll call this resistor EQ3. So this is the equivalent resistance at part 3, and so we're going to call this resistor C, and we'll call this resistor D, and so we'll do the same thing we did earlier. The equivalent resistance here is going to equal 1 over the resistor C plus 1 over the resistor D. Take that to the negative 1 power. So that is just simply saying 1/4 plus 1/8 to the negative 1. This is going to be equal to 3/8. We got to remember to take the inverse, and that's going to equal 8 over 3. In other words, when you solve that, it's going to equal 2.667 ohms. So now let's zoom out and get a sky view of what's going on. We have a resistor part 1, a resistor 2, and a resistor part 3. And now we can say that all of these resistors are in a series. And so if we want to add up the resistors in a series, the equivalent resistance for the resistors in a series is equal to R1 plus R2 plus R3. So this is basically saying just add them all up and you'll get your answer. So this is R1 is going to actually be the equivalent resistance at point 1, REQ1. This is EQ1, this is EQ3, and this is just resistor 2, which is 5. So we have a total of 5 plus 2.667 plus 4. So the answer here at part A is going to be 11.667 ohms of resistance is the equivalent resistance. So if I were to make another circuit called point A and point B, and I wanted just one resistor that would behave like all of these combined, I could get one resistor right here that would be 11.67 ohms, and it would do the exact same job. Now in part B, it asks the question, if a voltage of 41.9 volts is applied between points A and B, find the current for each resistor. For this is where everyone had problems on the last video I made, so I want to explain this in a different way. When you're using electricity, the equation you use is voltage, V equals I times R. The voltage is the driving force. The I, the current, is the substance moving, and the resistor is the resistance to movement. No, in medical school, there's a lot of cardiophysiology that's simplified, sort of like this. Whenever you're talking about blood pressure, you can say that the pressure in the arterioles or in the arteries or wherever, the pressure is equal to the flow, and usually flow is with a V, the flow times the resistance. So pressure is the driving force. The flow, which this is, don't get this confused with voltage. I'll go ahead and put an F for flow. Don't confuse it with force either. But the pressure, the driving force, is going to be equal to the movement times the resistance. So in the question, what it's giving us is it's telling us we have a voltage. We have a voltage across the entire thing. We know what the voltage is. It also says that we know what all of these resistances are. We know what all of those are, and what it's asking us is to find the electrons moving across each one. What is the rate that electrons are moving across here? What is the rate electrons are moving across here? What is the rate electrons are moving across here? You know, and so what is the rate that electrons are moving across each one of these resistors? Likewise, it could have given us a pressure. Let's suppose that we have blood moving into this artery, and we know what the pressure is moving in right here. And so the pressure, let's say right here is 100, and the pressure over here is 50. So the total pressure across the whole thing, the delta P, would be equal to 50. So that would be like saying that the delta V up here is equal to, and I think what it said something like 54 or 46 or something like that. It doesn't matter at this point. It's just giving it an idea. So we know what the total change in voltage is. We know what the total change in pressure is. We know what the driving force is. The driving force is the change of pressure. So if you have water that is under pressure, that has a high pressure in one place and a low pressure in another, it will always move from high pressure to low pressure until those pressures become equal. Likewise, if you have electrons that are at a high voltage, and they're connected to something that is at a lower voltage, they will move from high voltage to low voltage. Voltage is the driving force. In the arteries, we can get what the resistance is. The resistance in an artery is going to be, it's called Poiseuille's law. So you can calculate the resistance based on the diameter of the tube that the fluid is running through. So whatever that diameter or that radius is, you can calculate in the length. So it's the diameter or radius of the tube, the length of the tube, the viscosity of the fluid. All of those things contribute to the resistance of movement. And so the resistance here is basically how much is the wall of the vessel, or the wall of the tube, how much is the wall of that tube interfering with fluid moving. And then the current, or the flow, we'll call it the flow, is basically how much fluid is moving across this spot during a given period of time. So now that you have those ideas, one thing is very, very easy to figure out. That is the fact that whatever fluid moves in, so whatever fluid moves in right here is the exact same amount that has to come out here. So any part of this system that is in circuit will have the exact same flow. So if we could condense this down into one thing, the fluid moving in here, the flow here, is going to equal the total flow of this whole thing. It's going to equal the flow right here. It's going to equal the total flow, the equivalent flow of this whole thing, and it's going to be equal to the flow right there. And so let's think about that for the electrical circuit really quick. So it said that we had a change in voltage of 41.9 volts. And we know what our equivalent resistance, our total equivalent resistance, is equal to 11.67 ohms. So the change in voltage from here to here, 41.9, the total resistance from the same point is 11.67. So we can find the total number of electrons that go into here and the total number that come out of here. They're all going to be exactly equal at that point. So we can find that by just dividing. So V equals IR, you can just do I equals V over R. So we can find out the total flow of electrons through the entire unit. It'll give us the electrons moving in right here. It'll give us the electrons moving out right here. And we know that that will also be equal to the electrons flowing through this circuit. And if we could find some kind of equivalent flow of this whole thing, that would equal the flow of the entire thing. And if we could find an equivalent flow right here, that would also be equal. Now here's the tricky part. We know that we have a certain pressure right here being applied. And so let me change my color. So we have a pressure right here being applied. Some fluid flows that way and some fluid flows that way. What is the pressure going downward? What is the pressure going upward? And I submit to you that the pressures in both directions are the same. So here's how we can think of it. If we just zoom in right here, first of all, we know that pressure is equal to the force divided by the area. So let's just imagine that I have this little sliver right here, and that I have a force inside of it. That force has an area. The area includes both the top and the bottom, and so it has an equal pressure going up and going down. This is also going to be true for my electrical current. Now, here's where the analogy, the comparison breaks down, because in a water and in a fluid system, I have resistance every single step of the way. So every single little inch, I have more resistance. In a really, really great electrical circuit, you only have resistance where there are actually resistors. So you won't have a resistance here. So your driving force will not be decreasing along the way. It will stay even all the way up to the edge of the resistors. And then as it moves across this resistor, let's zoom in over to this side where it's a little bit cleaner. So we'll say that the voltage, we know what the voltage is right here, and it stays the same going up and going down. And so the voltage right here is equal to the voltage right here. The voltage on the top and the bottom are the same all the way up until they reach their resistors. Then as it goes across, the voltage has decreased some. And it's decreased some over here. We don't know how much it decreased. It depends on what the resistance and what the current is. And so now I think you have enough concept understanding that we can go back and we can solve this problem. Okay, so the first thing that we know is, if we look at this, we know the voltage from point A to point B is 41.9. And we know that the total equivalent resistance is 11.667. I want to know the current that moves in at point A, and I want to know the current that moves out at point B. It's going to be equal, right? And so if I start with my equation V equals IR, I can solve and say I is equal to V over R. More specifically, I can say that it is equal to 41.9 divided by 11.67. And you'll get that the total current, I'll just put a sub T, I sub T. The total current moving through the entire thing is 3.59 amps. So I know, remember that I said that if I have a current that is moving in here, so I have 3.59 amps. Some of that electrons are going to go up this way. I don't know how many yet. Some are going to go down this way. I don't know how many yet. But then when they meet up back here, they're going to recombine. So if let's say that I had 2 go up this way and 1.59 go down this way, I don't know. But then when they get over here, those electrons will recombine. I'll get the 2 here and the 1.59 here. They'll recombine and they'll start going through this resistor together. So 3.59 amps will move through this resistor, and 3.59 amps will move through the point B. So 3.59 in point A, split up over these 2 points, back together through here, split up again, and back together right here. So on the 5 ohm resistor, I can put 3.59 amps. Now if I wanted to at this point, I could come back and say, what is the change of voltage across this resistor? I could say, well, the current that went across it was 3.59, and the resistance is 5, and I could say that the change of voltage is equal to 3.59 times 5. Also, you remember I said that I could call this an equivalent resistance, and remember I said that it is the equivalent resistance of 4 ohms. And so I had 3.59 amps moving across this total section, and it was experiencing an equivalent of 4 ohms. And so the change in voltage in that section was equal to 4 ohms times 3.59 amps. That equals 14.36 volts. So as my current went from this point right here to this point over here, it lost 14.36 volts. And then as it went from this point here to this point here, it lost 17.95 volts. And if we make a little bit more room here at the bottom, we can also say that the change in voltage from here to here, we can say that the change in voltage from that area, remember that this entire area had an equivalent resistance of 8 over 3, which was 2.667. When you times that by 3.59, then you get that the total change in voltage was 9.575 volts. And if you add up all of these changes of voltage, go over here. If you add up all of these changes of voltage, then what you get is a number of 41.885. Now, so rounding in all of these numbers, we lost a little bit, but it's 41.9 volts changed, and that is what it tells us. It tells us that we had a change of voltage of 41.9, so we know that we did all of our math in each one of these segments correctly. Now here's why that was important to do. First of all, so we're going to zoom in. We're going to say that we had a voltage, a potential of 41.9. It came in. Some of it went straight up there. It went straight down here. And at this point, we have a voltage of 41.9. And then it goes over. When it gets over here, we don't know what the new voltage is, right? So we get over here. Right now, we don't know what the new voltage is. Well, as a matter of fact, we do, because we said that we know what the change of voltage is across that area. The change of voltage was 14.36 going from point A to this junction right here. So here's what I'm going to ask you to start thinking about fluid again, just momentarily. I know if I have fluid going in here, and it splits up and it goes across here, when it gets back to this side, it has to be equal. The pressure has to be equal once it gets here. The reason it has to be equal is because when it meets up in the middle, if the pressure is lower on the top, some of that fluid on the bottom will flow up and some of it will flow outward. If the pressure was lower on the bottom, the fluid on the top would flow down and go in both directions. So the liquid will always move from highest pressure to lowest pressure. If the pressure is not equal right here, there will be fluid movement backwards, or there will be fluid movement backwards this way. There's not fluid movement backwards, there's fluid movement forwards. That means right here the pressures are equal. And so I'm trying to say is, I know that my change of voltage across here is equal to my change in voltage across here, which is going to be equal to the equivalent change of voltage. And again, we said that was 14.36. So 14.36, if I put V equals IR, right? V equals IR, and I'm trying to find the current moving across here, then I do V 14.36 divided by 12 is equal to 1.197 amps. And then again, the same principle on the bottom, I could say that 14.36 divided by 6, that's going to equal 2.93 2.93 amps. So, and then we can check. So we're saying that when the 3.59 amps were here, 3.59 units of electrons were here, they started moving. Some of them went up, some of them went down. And then they went across here, and then they re-met up over at the other side. They re-met up over here, and when they did, they were 3.59 again. So we should be able to add these numbers up, and they should equal 3.59. And they don't is because I actually transcribed wrong. So 14.36 divided by 6 is equal to 2.393. But now when you add 2.393 to 1.197, the total is 3.59. And so let's back up and say, okay, it asked me about the 12 ohm resistor, how much current was going through that. That was 1.197. How much was going through the 6 ohm resistor? That was 2.393. And now I want to ask myself the question, how much, so I know I lost some current going from this point to this point, and then I lost some more. I'm sorry, I didn't lose current, I lost voltage. The current's the same all the way through, but I lost some of my pushing force, my motive force going from here to here. I lost some more of that going from here to here. And then, so how much pushing force do I have left? And I can look at that, it's really easy. So I know that my total change, the total change was going to be equal to 41.9, and I lost 14.36 going across the first area, and I lost another 17.95 going across the second area, and I know that in the last area I'm going to lose 9.57, so I know that this should equal 9.575, and in fact it does. So the voltage difference, let's zoom back in, the voltage difference moving from this point to this point is 9.575, and so I have 9.575 volts pushing here, and I have 9.575 volts pushing here. And again, my change in voltage divided by my resistance will give me the current that goes across each resistor. So my 9.575 divided by 4, and my 9.575 divided by 8. So this will equal 2.394, and this will equal 1.197, and again we know that these two numbers should add up to be approximately 3.59, and in fact it equals 3.591, so we know it's a rounding issue, but the current going across here is 1.197, and the current going across here is 2.394. So the current going across the 4 ohm resistor is 2.394, and going across the 8 ohm resistor was 1.197. Now I want you to notice something. The first thing I want you to notice is that at the 12 and 6, 1.197, 2.393 or 394, and then down here at the 8 and the 4, 1.197, 2.394. And what you'll notice is that, first of all, the total, these are resistors in parallel. So the total of these should equal 3.59, and they do. And the total of these should equal 3.59, and they do. But what you'll notice is that because the ratio of this resistor to this resistor is exactly 1 to 2, or 1/2 if you do 6 over 12, and the ratio here, 4 to 8, is equal to 1/2. So the ratio of the current going through each of these should also be the same. And because it's the exact same current, because you have the total, the exact same total current moving through the whole unit. And so I just walked you through the intuitive way to solve that. There's another way to solve that. There's this physics textbook, physics teacher kind of way to solve this thing, and that's by using things called Kirchhoff rules and loop rules. And those rules are basically just codifying what I showed you, how to connect the idea of electricity to the idea of water. The first rule is the the node rule. So if I have a split right here or a split right here, I know that the current going into this split, so I'll call it the I total, is going to equal the, I'll call the current going towards the top, I1, is going to equal I1 plus the current going toward the bottom, plus I2. So sometimes this is called Kirchhoff's first law, or Kirchhoff's junction rule, the junction rule, or the nodal rule, or the point rule. You don't need to know all that. You just need to know that some of the electrons are going up, some of the electrons are going down. So the total number of electrons going in has to equal the electrons that are going in each direction. So if there were another, connection right here, we could call that I3, then it would be the total current is equal to the current going up plus the current going across plus the current going down. So it's anytime there's a node where a bunch of things are connecting, you can say that the current going in equals the total of all currents going out. Now, intuitively, this seems as if it is based off of the conservation of mass. Now, you read the textbooks, they'll say that this is based on the conservation of energy, and that's both of those things are true. This is just the conservation of things, that the things going in have to equal the things going out. Now there's another rule called Kirchhoff's second law, or it's sometimes called the loop rule, or Kirchhoff's second rule, Kirchhoff's loop rule. So we're just going to call it the loop rule. And again, we'll zoom in to try to figure out exactly what this loop rule is. And so the loop rule, I'm going to get some, maybe some yellow. So the loop rule says if I start at any point, so I have this whole circuit, and I've got resistors in this circuit, and I've got this whole loop that's connected together. So I've got this whole thing connected together, and it says that I could start at any point on here. So let me start right here. And it says that as I move in any given direction, so if I were to move this direction and make one complete loop, the total changes of the voltage have to equal 0. The sum of all of the changes of voltage have to equal 0. I'll get to why that's intuitive in a moment, but let's say I go up, let me switch back over to the pencil and change the color to blue. I start right here and I go up and I go here, and then as I move across here there's going to be a change in voltage. So this is a change in voltage, and then I keep going and I go down and I go back this way and go across here, and there's another change in voltage, and then I go back to where I started. And so I have this change in voltage number 1 and I have this change in voltage number 2, and when I add those together they should equal 0. And so I have to keep in mind what direction I'm moving. And I'm moving in the opposite direction. So here I'm moving in the same direction as current, so current would be positive. And here I'm moving in, down here I'm moving in the opposite direction of current, so whenever I do my calculation, the current will be negative. And so if I go back and I just write down what the equation is, what it means, I say that delta V number 1 plus delta V number 2 is equal to 0. And then I will break this out a little bit, because delta V1, what is delta V1? Delta V, so delta V is equal to I times R, so this is the current in that first resistor times the resistance of that first resistor plus the current in that second resistor times the resistance in that second resistor. It has to equal 0. And you remember that the current in that second resistor is going to equal negative of the actual current. So we'll just put negative I. And you can actually distribute that, and you would get I1R1 minus I2R2. So we could divide that to the other, or subtract that to the other side, and we would have that I1 times R1 is equal to I2 times R2. And this is basically what I was saying to you. Why is this intuitive? I was saying to you that whenever you have a pressure drop when your fluid is moving through the pipe, the pressure, once it gets to right here, has to equal the pressure once it gets to right here, because if the pressure was lower going up, I would have some of my fluid go up and some of it would go over. So it's just saying what I said earlier, that once you get to this node, the pressures have to be equal. And so whenever you can go back and check and see if it all fits, I promise you it does, but that is basically all Kirchhoff's second rule is. And so how can I solve anything using these equations? So I came up with this equation, I1 times R1 equals I2 times R2, and I came up with this equation, I total equals I1 plus I2. Well, I don't know what any of these are, so I have to solve for a single variable. So I'm going to take this, I'm going to divide by R1 so that I can solve for I1. So I1, the current at that top resistor, is going to equal I2 times R2 divided by R1. Now I can take this and I can substitute it in anywhere I see I1. That's going to give me, if I come over here, I'll say that the total resistance, or the total current, I total, is equal to I2 times R2 divided by R1 plus, slide this over again, plus I2. Now I am down to one unknown variable. I know what the resistance are. It tells me what they are. I know what the total current is because I was able to solve that, saying that the total current is 3.59. So really quickly, I'm just going to rewrite this in a way that makes the algebra a little bit easier. So the total current is equal to R2 over R1 times I2 plus I2. And now you can see I can factor out I2. So I get that the total current is equal to I2 times R2 over R1 plus 1. And then I can just divide this whole thing to the other side. And I will find out that I2, so if I say I2 is equal to the total current divided by R2 over R1 plus 1. R2 we had as 6, R1 we had as 12, so we have 1/2 plus 1 is 1.5, and that's over the 3.59. And that tells me 3.59 over 1.5 is equal to 2.393. I almost made the same mistake I made earlier, 2.393. So 2.393 amps moving across that second resistor, the one we said is 6 ohms. Now it's really easy because I already solved what I1 was earlier. If you remember, we come back and say, I know what the total current is 3.59. The current in I2, make my pen a little bit smaller, the current in I2 is 2.393, and so 3.59 minus 2.393 would give me I1. It would give me the current moving across the 12 ohm resistor. And then for the next part, we would have to do the same thing. We know that there are 3.59 amps of current going through there. We'll call that the total current. Again, the total current would be equal to the current going up plus the current going down. And then we don't know what any of those are yet, but we also know that if we start at any point in here, if we start at, say, this point right here, and we go up and go down, we'll have a delta V. This is going to be, let me change that to green. This is going to be delta V. So I started right here, up over delta V. Then I'm going to go down, and as I go across that resistor, I'll have another delta V, and then I'll keep going and I'll be back where I'm at. And so this delta V is going in the same direction as current. This delta V is going in the opposite, so my current will be negative. I is equal to negative of the actual I. You know, just remember that it's going to be negative. And so you'll say that this is delta V1, delta V2. And then you'll do the same thing all over again. So let's go ahead and do it really quickly, just so there's no confusion. I have that delta V1 plus delta V2 equals 0. And I say that delta V1 is equal to the current at point at the first resistor times the resistance at the first resistor, and then I can put a minus because my delta V2 is going in the opposite direction of the current, so minus I2 times R2 equals 0. I can just subtract this over to the other side of the equation. I1 R1 equals I2 R2. I can solve for I1. I1 equals I2 times R2 over R1. Then I just plug this into my equation anywhere that I see I1. And what was that equation? It was that the total current is equal to I1. So instead of I1, I'll put I2 times R2 over R1 plus I2. In other words, my total current is equal to I1 plus I2. If I go back and factor out I2, then you remember, factor out I2, I get that the total current is equal to I2 times R2 over R1 plus 1. And then I can divide this to the other side, and I'll get that I2 is equal to the total current divided by R2 over R1 plus 1. Don't let this confuse you. If you don't stop and think about it, it might confuse you. So you get, I'll go ahead and plug in. So R2 over R1, that's 8 over 4, so that's going to be equal to 2 plus 1 is 3. So the total current, 3.59 divided by 3 is going to equal I2, which is 1.1967, or you can round it prior to that, but 1.1967, 1.197, whatever you want to do. And you say, wait a second, I thought that the I2 was larger. Remember, so the larger one over here was on I1 was the R1. The larger one over here is the R2. And so we are going to have a lower current whenever the resistance is high. All right, just keep that in mind. And so now you just, to find I1, it's 3.59 minus 1.19667, and you know what that is, 2.393. So now I've given you two ways to solve this problem. I've been very lengthy and wordy, and so if you have any problems, I'm sorry, that's the best I can do.